Hello everyone, I am Sodis Constantino from University of Cyprus and I welcome you to the presentation of the IoT Meta-Control Firewall. According to studies, it is expected that the number of IoT devices per house will drastically increase to more than 500 smart devices by 2022. The European Union aims to be climate neutral by 2050, an economy with net zero greenhouse gas emissions. This objective is at the heart of the European Green Deal and in line with the European Union's commitment to global climate action under the Paris Agreement. Unfortunately, the CO2 pollution of information and communications technology is expected to rise from 4% to 8% by 2025. Many IoT devices enable the execution of rule automation workflows, which span from simple predicate statements to procedural workflows, capturing a smart actuation pipeline in tools like IFTTT, Apelio, or Apple Automation. The rule automation workflows aim to meet the convenience level of users under specific conditions. However, none of the above raw technologies enables individuals or group of users to express their convenience or comfort preferences while achieving some long-term objectives. Consider, for example, a family with a yearly budget of 8,000 kilowatt-hours that aims to spend this energy budget through rule automation workflows based on their configured energy consumption preferences. The family is willing to adapt its desired interior temperature preferences according to production patterns, but has no clue how the raw pipelines contribute to the target of using only 8,000 kilowatt-hours per year. Our aim is to optimize both convenience and energy consumption objectives at the same time. Here, we see a breakdown of our applied algorithms. The no-rule approach does not modify the behavior of the autonomous devices. Therefore, the energy consumption is minimum and the convenience error is maximum. The meta-rule algorithm satisfies all rules set by the user by completely ignoring the energy consumption. Therefore, the energy consumption is maximum and the convenience error is minimum. Furthermore, the if this then that approach executes the IFTTT preferences configured by the users. And finally, the energy planner algorithm executes rules considering the trade-off between the convenience and energy consumption. Specifically, the amortization plan is initially executed for calculating the energy budget constraint subject to a monthly resident's energy consumption profile. There are several amortization strategies that can be used, such as the linear, balloon linear, and the ECP-based amortization formula. The energy planner utilizes the well-known hill climbing approach, such as a decision space for a solution that will optimize the user's convenience and satisfy the energy constraint at the same time. However, any kind of heuristic or meta-heuristic approach can be utilized in the EP optimization step. Consider the simplified scenario in which a user sets 4 meta rules in the meta rule table, which along with some input data from the house's sensors as well as some online web services are forwarded to the IMCF. Then the IMCF converts the meta rule table to a binary vector in which each position of the vector represents a meta rule. Where the value is equal to 0 at position I means ignoring meta rule in that specific position, and where the value is equal to 1 at the position I means adopting meta rule in that particular position. A random initialization process generates the first solution, which means that meta rules 1 and 4 will be triggered and meta rules 2 and 3 will be ignored. The solution is evaluated using the performance metrics of the energy consumption and convenience error. During the optimization, 2 vector components are modified using a uniform random generator. In this example, the value of vector component 2 is swapped from 0 to 1 and the value of component 4 is swapped from 1 to 0. The new generated solution is again evaluated and compared with the current best solution. At each iteration, when solution S is better than solution S star, then S becomes S star. A solution is considered better and replaces the current one when the energy consumption is less or equal to the energy budget constraint, and also when the convenience error is less than the previous best solution. The energy planner stops when the configured number of iterations are completed. Our system architecture comprises of a full-fledged local controller implemented inside the OpenHub stack, which is a smart home management software, and IMCF, which is the software system that encapsulates the complete application logic of the energy management stack we propose, along with the respective user interfaces. The local controller is a Java-based system installed on a micro device running on the local network of a user that will be in direct communication with the IoT devices through the OpenHub smartphone application. The complete picture can tentatively be complemented by a cloud meta controller, which can enable the user to configure and run various custom rules. The IMCF has been implemented using the Open Home Automation Bus, the Linux cron tab daemon, the Anyplace for built-in modeling, as well as the Laravel PHP web framework following the Model View Controller architectural pattern. The graphical user interface records OpenHub smart device measurements on local storage and presents them on a table. It allows users to configure various meta rules in regards to kilowatt-hour limit, temperature, and light values. It also operates the IMCF framework and gets an efficient execution considering user satisfaction along with the balanced convenience error and energy consumption. Finally, it demonstrates the results on a user-friendly graphs. We have evaluated our design with extensive experimentation on real datasets with anonymized measurements from a real residential apartment that comprises of a variety of sensors, sub-meters, and approximately 5 million readings collected by the Center for Advanced Studies in Adaptive Systems at Washington State University. To evaluate the scalability of our propositions for residential buildings of various scales, we have generated 3 realistic datasets by replicating the above onto various building sizes: a flat, a house, and a dorms dataset. Our cost metrics for each meta rule are the convenience error, which is the difference between the desired output value and the actual value, the energy consumption, which is the energy consumption of a device, and the CPU time, which is the processing time required by the controller for running the optimization function and calculating the output for all meta rules. In this experimental series, we evaluated the performance of the proposed EP framework against all algorithms over all datasets introduced with respect to energy consumption, convenience error, and CPU execution time. The no-rule approach obtained the worst convenience error of 62% and the best energy consumption. The energy planner obtained an impressive convenience error of around 2 to 4% and the second lowest energy consumption. The IFTTT and meta rule approaches are greedy in regards of energy consumption. The meta rule algorithm satisfies all the meta rules, thus its convenience error is 0%, which is the best possible obtained. Worth mentioning is also the fact that the energy consumption difference between the meta rule and energy planning algorithm is relatively high. The fastest execution time was achieved by the no-rule approach, since it simply executes an error calculation ignoring all rules. The energy planner hill climbing approach searches the decision space for a solution that will optimize the user's convenience and satisfy the energy constraint at the same time, which is a much more time-consuming process. Finally, the meta rule approach focuses only on minimizing the convenience error, which means executing all meta rules without any iterative processes or calculations, since the convenience error is 0%. In the second experiment, we evaluated the performance of the proposed energy planning framework against different rule modifications with respect to energy consumption and convenience error. The figure illustrates that by using 4 activation-deactivation rule modifications in each iteration, we obtain the best convenience error. The worst convenience error occurred when we used 2 rule modifications. The convenience error decreased as we increased the rule modifications in each iteration. This is due to the hill climbing approach performing bigger jumps towards the local optimum at each step and thus searching the solution space more effectively. As the number of rule modifications increases, the convenience error is decreasing gradually while the energy consumption is approximately at the same level. In the third experimental series, we have evaluated the performance of the proposed EP framework using different initialization strategies. In the first case, we have initially activated and applied all rules. In the second case, we have uniformly randomly activated some rules. In the last case, we have initially deactivated all rules. The figure presents the convenience error that increases by using the all deactivated rule strategy, hence consuming less energy, in contrast to the all activated and random rule strategies. The hill climbing approach needs to perform more iterations in the solution space to find the local optimum and consequently an optimal energy plan when all rules are deactivated. In the fourth experimental series, we have evaluated the performance of the proposed energy planner approach over various savings percentages. This evaluation is inspired by the SAVES project an inter-dormitory energy-saving competition that took place on 2014 to 2016. SAVES aimed at delivering 8% average electricity savings in participating dormitories. The figure shows that by increasing the potential energy savings, there is a slight increase on the convenience error, clearly demonstrating the trade-off between those two objectives. In the final experimental series, we have deployed an instance of our real prototype system for a family of 3 persons for 1 week. Each person configured their personal preferences using the mobile app that interacts with an IMCF local controller node on a Linux virtual machine on our data center. In order to measure the environmental parameters, we use data from the OpenWeather API. Our observation is that the energy planner is indeed an efficient approach for retrieving great user satisfaction, as it performs in 4 seconds on average with an average convenience error of 2.35%. The energy consumption is within the preferred budget limit as pre-configured by the user, and the system behaves correspondingly. The second table demonstrates for each individual resident their own average convenience error values in respect with their configured meta roles, showing both a consistent and high satisfaction close to 97.6% for all residents. The IoT Meta-Control Firewall is an innovative system architecture and application which internally deploys an AI-inspired energy planner algorithm that exploits domain-specific operators to balance the trade-off between convenience and energy consumption while managing raw pipelines of users. Using extensive real traces from an apartment, a house, and a campus, IMCF shows that a user can have 10% energy savings at only 2 to 4% decrease in the user's convenience. The execution of an energy planner is fairly fast, carrying out the computation in about 4 seconds for the largest datasets. Our approach requires no training data and only a primitive preference profile. And finally, it can be easily integrated in actuation platforms. This is the end of the presentation. Thank you very much for watching.